Hello and welcome back to another lecture. In this lecture, we're going to talk about moment distribution, how we're going to analyze indeterminate structure like this one. Just take a look at this structure, for example. We have this beam and it's fixed on both ends, and you got two roller support in the middle. And the distance between a fixed end and one roller is 12 meters, and between two roller is 12 meters, and then we have a constant load who split this 8-meter distance apart. We have 250 kilonewton down here, and then we have 20 kilonewton per meter for uniform distributed load. We want to know what is we like to know what is the moment at each different location. So we're going to analyze this using moment distribution. When you do moment distribution, first go ahead, Excel is the best way. Go ahead, pick out your Excel. By the way, I want to tell you this is a very important topic to learn if you're doing structural analysis. I guarantee it will be on a test and it will be on an even final exam. So pay attention to it. You got plenty of time. If you have to play the video over and over until you get it, then let's be it. All right, let's go to work. What we have here is, before we start, we're going to go ahead and make a chart. Let me bring up the Excel sheet here to see if I can do this. Perfect. So we make an Excel sheet, and I'm just going to, Excel sheet is over here. So I'm going to explain what we do. First, we're going to go by the joint. And we have joint. We have joint A, B, C, D. So I'm going to write down joint A, B, C, D. And then I'm going to go ahead, we have the member. We have different member. We have member, we got member AB. Then we got member, looking at the whole member. We're going to look at both ends of the member. So I'm going to go member AB. Then I'm going to get to the end. I'm going to look at member BA. Then when I look at the member, we have BC. Then I go to the C. I go look back. We'll go CB. Similarly, same thing we have in the last section. We have a member CD. And then we're going to look back, we're going to say DC, and that's what we have in these different joints right here. Actually, good. Now we're good to go. Then we're going to go ahead and find the distribution factor. What is distribution factor? Let's talk about, let me bring the PowerPoint up. Distribution factor. So if we look at the member stiffness, which we talked about, K is equal, the stiffness member K is equal 4EI divided by L. And when we look at the area, like for example, this here we have this joint A, which is basically 3 member coming into it. And the stiffness, and each member has its own stiffness factor of K, and basically K is 4EI divided by L, assuming EI is constant. You know, it's the same steel and same cross-sectional, so you'll be 4EI constants, so the length is going to be different. And each one of these, so that's going to have the KAB, and say came out to 4,001 and came out to 1,000 and the other member, and came out to 2,000 for member KEC. So now when we look at the distribution factor, is basically how many percent of, if you total all these K factor, KT, which we total of all the Ks, and then you're going to say how many percent of it's going to be on this side, how many percent that, and how many distribution, basically distributed, how many percent each member have of the total. So that's what the distribution factor is. And basically the distribution factor is K divided by the summation of K. So what I have done here, I'm going to have this, in order to solve the moment distribution, I came up with like 7 steps. We're going to follow these 7 steps. The first step was that the joints on a beam should be identified, which we did that. Second step, we're going to compute the distribution factor on each joint. So let's go ahead and do that. Point right here. One thing I want to bring up to attention, it says compute the distribution factor of each joint, which is basically is a K divided by summation of K. However, distribution is equal 0. Distribution factor is 0 for a fixed end member, and the distribution factor is equal 1 for a pin or a roller supported. Okay, let's go back and calculate the rest of the distribution factor here. So I'm going to So K AB is equal 4EI divided by 12. In our problem, this problem, the EI is constant. So KAB, now we're going to look at KBC and then KCD. KBC is equal 4EI divided by 12. The length is 12. And KCD is equal 4EI divided by 8. Okay? Remember, we look at each joint. Because that's a fixed end at joint A, we said, okay, distribution factor for this is 0. And also this is a fixed end. So the distribution factor also here is going to be 0. So those two is 0. And now we're going to come back in here. We're going to find out what's the distribution of BA and BC. So the total of AB and BC, they both equal, okay? Summation of KAB plus KBC is equal basically 2 times. Well, let's do this different way a little bit. All right, let's say that distribution factor we said is equal K divided by summation of K. So distribution factor for joint B, it's going to be, and I'm going to say for BA, it's going to be, for BA, for AB, it's going to be 4EI, and divide that by 12, and divided by the summation of both of them, plus 4EI divided by 12, and that becomes 0.5. So this is 0.5, 0.5, and obviously they got to add up to 1 anyway, so that's going to be 0.5 also. Or you're going to go ahead and use the same thing. This, you got to remember here, be careful. A lot of my students got this backward. So we're going to say 4EI divided by 12 divided by 4EI divided by 12. If we say, if divide everything by 4EI, and this is going to be 1 over 12 divided by 1 over 12 plus 1 over 8. So you got to flip this. If you just go ahead and say, no, it's 12 divided by this, not going to, that's become 0.4. Use your math, see if you figure that out. And so that becomes 0.4. Here I'm going to have 0.4, and then of course the rest of this one should be 0.6 to make it 1, and that's a 0. So that's our distribution factor. So let's go to the next step. And the next step is bring up back the PowerPoint. It says compute the fixed end moment for each loaded span using the table, and we're going to use the table. And the tables are, you know, I had the table right here. Let me go back to the PowerPoint. These are fixed end table. There's any book in the back of your book, any steel book, or just Google. You can find a fixed end moment for a lot of shapes like this. So we're going to use these fixed end moment. All right, let's get back to work here. Okay, we're going to go ahead and calculate fixed end moment. So first we're going to go ahead with a fixed end moment of BC, and look it up in the table, and that's basically is minus WL squared divided by 12, which is equal to be right here. That's a BC. There's nothing in there, so that's 0. So it's going to be minus 20 times 12 squared, divide that by 12, and that's going to come out to be 240 kilonewton. 240 kilonewton meter. Then we're going to find the other end, so it's going to be positive, so it's basically 240 40 kilonewton meter. And we're going to find the fixed moment for CD. It's a minus PL divided by 8. And these are come from a table. And P is 200 minus 250 time L is 8. And divide that by 8. And that also it's going to come out to 250 kilonewton meter. Run out of ink here. And the next one is fixed in moment. DC, which is basically PL divided by 8, and that comes out to 250 kilonewton meter. This is a negative, by the way. So let's go ahead and fill our hole here. We had fixed in moment. So this joint A has nothing, and BA has nothing. BC came out to be minus 240. That's a minus right here. So BC is minus 240. All right. And CB is 240 positive, 240. And CD came out to be minus 250, minus 250. And this one is a 250. Okay. So I'm going to just go ahead and say this is a 1, 2, 3, 4, 5, 6, 7, and as we go along. Go back to the PowerPoint again. Going back to this step, I want to explain the step we're doing. So the next step is over here. So our next step is compute the fixed amount you did, and then assume that all joints are initially locked. Okay, fine. Then determine the moment that is needed to put each joint in equilibrium, and release and unlock the joint and what they mean by that, and then do the carryover factor. We get to step number 7 in a second. Just so we go to step number 4 to number 6. And what we do here is lock and unlock moment. What do you mean by that? We're going to start with row number 5. I'm going to come in here. We said each joint has to be in equilibrium. This has to make this equilibrium has to be put minus 250 divided and then multiply the distribution factor, because the distribution factor is, so just leave it blank, that's a 0. So we're just going to put a 0 here. This is minus 250. So I'm going to say joint C. Let me write down here so we know what we're doing. Joint C. And we're going to say in joint C, the total moment in joint C is minus 250 and 240. So I got 240 minus 250, and that gave me minus 10. So I got to unbalance minus 10. That means I got to come up with a 10 to balance this joint to make it equilibrium, to make it 0. But 10, 40% of it got to come from CB, and then 60% of it got to come from, I lied, 40% got to come from CB, and 60% got to come from CD. So that 10 times 0.4, we all know that's equal 4. So there's 4 of them come from here. And then 10 times 0.6 is equal 6. And 6 of it come from here. So that balance out. So the total moment right here at the joint C becomes 0. If you add this, that becomes 0. Let's go to joint B. Joint B, the same thing. All we have is a minus 240. So I got to add 240. Where this 240 going to come from? Well, 50% come from BA, 50% come from BC. So 240 times 50% become 120 here. 240 times 50% become 120. 120 plus 120 become 240. 240 minus 240 becomes 0, so we balance that. And there's nothing here. Oh, we did this, we got to do carryover, because what do I mean by carryover? Let's go back to step number 7. Let me bring it up. Step number 7, it says right here, carry these member over to the other end of the member by multiplying each member by the carryover factor of plus 1/2. What do you mean by that? Let's talk about that. Whoops. Okay. So CD has a carryover as 6. CD, what is CD? CD right here has a carryover 6. So now we got to go ahead and go to the other end member and put half over here. So that's what we're bringing CD right here, bring it back to DC, and give it a 3 right here. Okay, that's half. 6 times half. That's step number 7 on the PowerPoint. Then we're going to come in here. We have CB, and CB got to go to the other way, give it to the BC. So that's going to be 4 times half, it'd be 2. At the same thing, we have BC, which has 120, got to give half to its buddy, CB, which is 60. Okay. And then here, a BA is 120, got to give to AB. On the other end, half of it, so that's 60. So now that's a carryover. Now we're going to start the process over again, balancing the joint. Okay. So we're going to go back to line 7. All right, so now we're going to come back and do the same thing here. This, it can balance itself because the time distribution says 0, so that's underneath it. It's going to be 0. We don't care about that. In here, at joint C, we have to put equilibrium joint C. So our moment is 60. To make an equilibrium, what? We've got to add minus 60 to make it 0. So again, joint C right here, at line it says 60. I need minus 60 to make it 0. So the total here is 60. So minus 60, 60% of it is going to come from here, and 40% is going to come from here. So 60 times 0.6 is minus 36. 60 times 0.4 is 24, minus 24. So minus 24 plus minus 36, make it minus 60. Minus 60 plus 60 becomes 0, so I balance this joint C, made it 0. I'm going to come back to joint B. Joint B, all I have is a 2, so I need minus 2. That means half of it, 1 minus 1 half come from here, and minus 1 come from here. So now I balance that 2, that becomes 0. Here, is distribution is 0, so it doesn't matter. That's a 0, because times the distribution factor. So now I'm going to go ahead and do the carryover. Again, this is going to go right here, and this is going to go right here, and this is going to go right there, and this is going to go right there. So minus 36, it makes it minus 18. And here, minus 24 may give me minus 12. And this give me minus 0.5. And this give me minus 0.5. Okay. So now we did this, and we're going to go ahead and start the process over again. Now we're going to balance based on the distribution factor. I'm going to start the process over again in the line number, let's call this line 8, 9, 10, 11. There should be carryover distribution, maybe 12, 13, 14. We'll see if you can finish with 14. So I'm going to come back and do the same thing here. This is balanced, basically it's going to be 0. This right here, this joint C, the joint C right here, all I have is a 0.5, minus 0.5. So I need plus 0.5 to make the balance this joint to make it 0. The plus 0.5, 60% come from here. So 60 be 0.3 I believe, 0.3. And the other 60 will to 40% be 0.2 right here, 0.2. So that was 0.5, that makes it 0. In here I got 12. So 12, that means 6 got to come from here, and 6 got to come here. 6 and 6 is 12. 12 minus 12 becomes 0, so that's balanced. Okay, this doesn't have to be balanced because the distribution factor is 0. Now we're going to go back to crossing again. So I'm going to go ahead and let's use a different color here. I think just alternate between blue is good. So this is going to have to be 50% of this has to go to the other end of the member. And that's going to be basically 3. And I don't like this color, but it will do fine. And then we go to B right here. And that's going to be the same way. Follow the same pattern. That's going to be 0.1. And that's going to be 3. And that's a 0.3. That's going to become 0.15. Continue with the balancing now. This is basically 0 right here, balance itself. Joint C, we have, all we have is a 3, so we need minus 3. Minus 3 times 0.6. That is minus 1.8, and then 1.2 minus 1.2. So that makes it 3. That's a 40%. 3 times 40 is 0.4 is 1.2. 3 times 0.6. So now we add this 2 plus this makes it 0. That's joint is balanced. Come back in here at joint B, all I have is a 0.1, so I need minus 0.1. So that's going to be minus 0.05 and minus 0.05. So that makes it 0. And then I will do the carryover right now in a second with a different color. So we're going to do the carryover again, coming this way, and that's going to be minus 0.025. And in here we're going to have the same thing, and minus 1.2 give me minus 0.6, minus 0.025, and that's going to come in here, give me minus 0.9. Pretty close. When these become very small, then we can stop. So let's do one more time and balance the distribution. So that becomes 0 anyway. And we have all we have here in this joint is minus 0.025. Minus 0.025 times 60% is, so let's just say minus 0.01, plus 0.01. To balance this is plus 0.01, 0.01, and 0.0115, and it's going to become 0.01. It's so small it doesn't matter. So now we're going to go ahead and go to joint B. Joint B is a 0.6, and so that means 0.3 come from here, 0.3 come here, and this is 0, and we just leave it like that. Then we're going to go ahead and sum it. And I did this on Excel, so let me bring the Excel sheet up and we can take a look at it. Okay, I summed it at the Excel sheet. I'm just going to copy down the Excel sheet right as we have them right there. Can't see that. Okay. I got 6248. 6248. Let me write a different color here. Go green. And then we have 125.25. Okay, the next thing I'm going to come in, I'm going to take these and cut them to pieces, put AB right here, put BC right here, and put CB right here. And when I cut them, I'm going to replace them with moment and share, moment and share, moment and share. Everybody asks in the class, but why is it turning this way? Why is it turning the other way? Well, let's pay attention here. Let's start off from this end. We got 250 kilonewton. Let me bring this up here. This 250 coming down, so it's going to take a moment about 0.8. It's going to turn like this. Okay? Now the ends, again, has to do the opposite, kind of support that, to kind of fight it back. So it's going to go the opposite of this. That's why it's going over like that. So this right here, taking a moment about this end, and it's going to go this way. Okay? So this got to go the opposite way. And obviously we have this coming down, and the reaction going to be up here, and one's going to be up there. That's how you get it. So that's all why we have all those in there. And remember one thing also, clockwise is positive on these here. Clockwise is positive, okay? And we're going to go ahead and label this already. Based on our table right here, so we have, this one came out to 234.3, and it's positive because it's a clockwise. Different color here. 234.3. 234.3, and this one came out to be 81.5. minus 281.5. Okay, and up here that's going to be clockwise, it's going to be 281. That's a CB 281.5. So that's positive also because it's clockwise, 281.5. And this number gave us also the based on here. And then the other side, which is a BC. BC came out to be minus 125. And this is going to be also up there. That's the same as a BA. BA 125.25. 125.25. And this one came out to 62.4. 62.4. So now we have that. Okay, now we got those individual. I'm going to go ahead and calculate these shear values. So I do only one of them, and you can figure the system out yourself. Let's do the joint A. I'm going to take a moment about point B. Take a moment about point B. So I'm going to say summation moment about point B is equal to 0. Counterclockwise is positive. This is different than that. This is just for our own sign convention to solve this equation here. I'm saying whatever I use here, counterclockwise for me is a negative. Okay, so I'm going to start from here, taking about, so that's a clockwise, so that's minus 62.4. And then I have AY. AY is going to take a rotation about point B, counterclockwise, so it's a plus AY time, and that's a 12. And then I have nothing else I can treat here, and this is basically clockwise, so it's minus 125, minus 125.25, and combination all come out to 0, and therefore these two combined divide by 12, and that will give me AY. Check my number. I double check it myself too. 15.6. So this right here become 15.6 kilonewton. And if I do summation F of Y, there's no load here, so this also becomes 15.6 kilonewton. We do the same thing right here. Let me just do this one, and then we do that one. I'm going to take a moment again about point B. Summation moment about point B is equal to 0. Counterclockwise is positive. I have the 125. It's a counterclockwise, 0.25. And then that's going to take a clockwise, so it's going to be minus BY times 12. And then I'm going to have, this will be the constant load, that will be right here. So be, and it's going to take a counterclockwise, so it's going to be plus, is it 220? This is not right. This is 20 kilonewton. This is 20 kilonewton. So it's going to be plus 20 times 12 times 6. And then this one is going to be basically clockwise, so it's minus 281. Minus 281.5 equals 0, and BY comes out to be, double check my numbers, see if I got that right. 7 kilonewton. 107 kilonewton. And if you do summation F of Y, and your AY comes out to be, BY comes out to be CY equals 0. CY comes out to be 133.3. So this came out to be right here, 107 kilonewton, and this came out to be 133.3 kilonewton. Do the same thing over here, just give you the answer, you can figure it out yourself, it's not that hard. So this should come out to be 130.9 and 119.1 kilonewton. So there's all our information here. calculate all the shears and moment on each section. Remember, we took this, we cut it right here, and then we cut the individual pieces and we put these in here. We can take advantage of this, take this, and draw the shear moment diagram. Let's go with the shear, because to do the moment diagram, it's really, go to it directly, it's not going to be easy. Shear diagram helps a lot. So I'm going to come up here, look at the first section right here. My shear dropped at 15.6, we knew that. So I'll come down 15.6. Nothing going on until I get back to this end. Remember, because this is a cut, it's different than usual shear moment diagram. So when I get to this end, I'm going to come back up 15.6. So I'm going to come back up 15.6. Now I'm back to this section here, which is over there, and that says it's going to go up 107, and I go up another 107. And then I'm coming down 20 kilonewton per meter. So I'm coming down 20 kilonewton per meter, and that time 12, it brings it back down to 133, which we already know that, 133.3. I forgot the 0.3, no big deal. Then once we get here, and we're going to go ahead, we're going to come back up 133.3 makes it 0, and then we're going to go up another 130.9. So now we got here, there's nothing going on until we get to this point, which is this point right here. Then we're going to drop down 250, that will bring us to 119. Then we want to get here, we come back to the reaction here, come back 119, and that's your shear diagram. But let's figure out, feed, where this point right here is. I need to know that, because pay attention to this. This is very important. Where your shear is 0, you have the maximum moment. That's rule. Remember that. Okay, so right here, which is this, shear is equal 0. So that's easy. That means the shear at some point, if I redraw that, I have a point like this, okay? And I have these load, which is at 20 kilonewton. What if we say at x, distance x, my shear right here becomes 0? I don't care about the moment, I'm just doing the shear. All I know, reaction at this time was, and here was 107 kilonewton. And this become, obviously, this is 20 kilonewton per meter. At the distance x, become 20x. That'd be the 20 times x. That become right here. That'd be a 20 times x right there. So this is a 20 times x. Take this out. Perfect. So summation if y is equal to 0. Going up is positive. I have 107. I have nothing else minus 20x. And this is 0 plus 0 equals 0. So x is equal 107 divided by 20. And so this become 5.4 almost. So this distance from here to here is from here to here is a 5.4. So if this is a 12, 12 plus 5 is 17.4. So let's say this distance 17.4 from here. And we good. So now let's go take a look at this one here. When we complete this, the moment diagram, we follow the same thing. I have the moment coming up 62.4. Then we're not going to go to this moment. We're going to go to this one, just like we did with the shear. This will balance it out. This will bring it back where we want it. So now it goes from here to minus 125. And because it's nothing there, so it's a linear, it's going to come down to minus 125. But once we get here, we're going to go from this moment to this moment here, because this will balance it out. This is where we're going to be. So we're going to go from minus 121 to minus 285. But how are we going to get there? Not going to get like this. Because of this will help us, it says, okay, you got to max out first, then you're going to come back down to it. And that's why we did. If this is a linear, this is a second degree curve, parabola. So we came from here, we come up here, we came on down here. All we know is this distance. We know this distance, which is a 17.4. I don't know this distance here. I don't know this distance, and I don't know this magnitude. Let's find those out, and we take care of that. Let me erase this right here. The property we're looking for, we know moment is 0 right here, moment is 0 right here. So we're going to use this equation right there, and actually it's drawn up, so that's pretty good right there. So we're going to say at some point when we have is 107, This is 125.2, and we're going to have a moment right here, this moment that we're going to put down, that is a mx equals 0 at point of x. And we have 20x and we have x, and this is the magnitude of this become 20 times x, and it's going to be distance x divided by 2 from the end. So if I take a moment about point x, summation moment about point x is equal, let's say counterclockwise is positive for our own thing. So this is going to become 125.2, I believe that's a 125.2, right? And then we're going to have this going to take a clockwise, so this is going to be minus 107 times x. We're taking a moment about this point, so we have this one, we have this taking a moment about that point, then we have this also taking a moment about this point. So that's going to be plus, so it's going to be plus 20 times x, and the distance is going to multiply as x divided by 2, and then this is 0, so say this equals to 0. And now if I redo its equation, it becomes basically 10x squared minus 107x plus 125.2 equals 0. What is this? This is quadratic formula. You already know this. So look it up, the quadratic formula, and let's plug this into quadratic formula, and I find out x1 is equal 1.35, and my x2 comes out to be what do I have here? 9.35. Remember, that's a distance from here. So for here, the 1.35 plus 12 makes it 13.5. So this distance becomes 13.35, and this distance is 9.35 plus 12. It makes it 21.35. 21.3. So now we found that. I want to know what the magnitude over here, the maximum moment. Let me erase this, and we go to the maximum moment. So our maximum moment happened at the distance of 17.4, which became 5.4 from here. So if I go ahead and plug mmax at x is equal 5.4. Remember we calculated this. This is 5.4 from here. It might be 17.4 there. So I'm going to go ahead, okay, 125.2 minus 107 times 5.4 plus 20 times, that's a 10x squared actually, plus 10 times 5.4 squared equal. And calculate that. Is equal, double check my number, 160.9 or 161. So this become right here become 160.9. All right, I leave this one for you. I give you the answer 242. 242. See if you can figure that one out. And how do I get that? I give you even a hint. So you're going to come in here. You're going to take a moment at the distance of 4 feet. So what are you going to do? You're going to say, okay, what's the moment at the distance of 4 feet? Let's do it. I think the guy's going to do it. The moment at the distance 4 feet is summation moment. Let me write that in a different color so it dries up with that one. Okay, at 4 feet in here, because we said this is a, what's this distance? This distance was, that's 8 feet, yeah, 4 feet. So I'm going to have minus 281.5 and minus 130.9 times 4. Actually, just put plus. If I go like this, this be plus. So that makes sense. Let's see what this distance come out to be. 1. All right, so I get 242.2. 242.2, and that's what it is. Okay, so this is how it's done. Please review this. This is a really good example. And if you like it, don't forget, give me a thumbs up. Have a good time. Take care.